Hello and welcome to homework 3. In this homework we will be talking again about the problem that we did in homework 2. So if you did not watch the homework 2 video, the last part of homework 2, I would suggest watching that video just to give some background before we jump into this problem here for homework 3. But just to give a general overview of what we looked at, we had a continuously stirred reactor here with some flow rate going in that had some concentration of A, and that concentration of A reacted to form B, and this was an exothermic reaction. So we had some coolant, basically a coolant jacket around our reactor that allowed us to cool the reactor down because it was an exothermic reaction and it was releasing heat, heating up basically as soon as the contents were reacting. So what we are asked to do here in homework 3 is to look at a similar scenario with an incoming stream, some concentration of A reacting to form B, and it's an exothermic reaction. However, we're going to be looking at a plug flow reactor. Now for a plug flow reactor, one thing that we can note here is that all this is just simply some series of continuously stirred reactors that we have here on the left. So in this homework, we're asked to break it up into 8 disk rotations, so 8 continuously stirred reactors. But just to give some sort of visualization here, we'll have all these different sections of the plug flow reactor, and we'll have the reaction occurring in one, and then the contents of that will be the inlet for the second reactor, and then the outlet of the second reactor would be the contents of the inlet for the third reactor. So this is essentially the same thing as if we have one continuously stirred reactor going into another CSTR, and then into another CSTR, and so on and so forth. So what we have here is that the differential equations for the concentration of A, the temperature, these are all essentially the same as a continuously stirred reactor. We just have to keep in mind that the outlet of one of the reactors is the inlet for the next one. So before we go into Python and we're going to simulate this, what we are asked to find is the concentration profile and the temperature profile of this plug flow reactor. Because obviously when we start reacting here, we're going to have different concentration here than we have here, than we have here, than we have here, and a different temperature at the start than we'll have at the back and in the middle. And also we want to see if we are running at some steady state, if we make any changes in flow rate or concentration of A going into the reactor, how will that change the concentration and temperature profiles of this plug flow reactor? So one thing to note here is that if we have 15 different disk rotations in our plug flow reactor, our volume, if we're assuming the same parameters, I think we used 100 liters of volume of our continuously stirred reactor in homework 2. So if we're doing 15 of these, we'll have to break our volume for each of these reactors into 15 if we're using the same differential equations, right? We'll have to divide this. So we'll have n is equal to 15, our number of reactors. And we'll also have our overall heat transfer coefficient, U, multiplied by the area. This heat transfer expression, I believe we had it at 50,000. And again, for each reactor, this will be divided by 15. So 50,000 divided by 15. So this is, I think, a good overview of what we are looking at here. Now let's go ahead and head into Python, and we can go ahead and start to simulate our concentration and temperature profiles of this plug flow reactor. Okay, so what I've gone ahead here and done is pulled up the problem that we are asked to solve, just to see that the initial parameters are just about the same for the same here as they were in homework 2 part C. So initially we have the plug flow reactor split into 15 continuously stirred reactors, And the contents across the board, across the entire reactor, are 350 Kelvin with 0.5 moles per liter of reactant A. And then the inlet feed going into the plug flow reactor has a temperature of 350 Kelvin and contains 1 mole per liter of reactant A. Coolant temperature is still at 290, and all the other same flow, reaction, and physical parameters from homework 2 part C apply. So what I've gone ahead here and done is just pulled up the same code that we used for homework 2 part C. Now obviously we'll need to change it quite a bit, specifically for our differential equations. But we can definitely use this as a basis to start, given that we have the same initial parameters that we used for homework 2 part C. So the first thing that we'll take a look at here is the initial parameters, and we're going to have to change the volume in both the volume and then the overall heat transfer for each of the continuously stirred reactors, because this time we have 15 of them and we're going to be simulating it across all 15. So what I'm going to do here is create a couple variables here. One, V total. So I'm going to set this equal to 100. So that's the total volume of the entire plug flow reactor, and then the total heat transfer, the overall heat transfer coefficient times the area, is equal to 5e to the fourth, or 50,000. And what we need to go down here and do, technically I could just divide this by 15, but if we wanted to change, say like the total volume of the plug flow reactor or the total heat transfer, it's just easier to do it this way. So we'll split our volume into 15. So these here are for each of the plug flow reactors. So we need to divide it by 15. And then likewise for the heat transfer here, we'll have UA total divided by 15. Okay, now, well, another thing we could do here is if we want to change the amount of continuously stirred reactors that we have, we can do this by setting an n value, so n for number, and we can divide this by n, right? So we have 15 plug flow reactor, or 15 continuously stirred reactors, right? So I think this takes care of our initial values here. Actually, no, we need to notice the temperature and the concentration here. Again, we have 15 continuously stirred reactors, and they're all going to have the same initial conditions, but we need to have 15 of those values. So what I'm going to do is create a full array, a size of 15, and put the value of each in the array. So if I go np.full, make it a size of n, so 15 is what we're setting it as, then put in 0.5 for the concentration. That's going to give us a full array, 15 values of 0.5, so one for each of the continuously stirred reactors. And again, likewise for temperature, np.full, size of n, and 350 Kelvin, right? Let's go ahead and make sure this runs here. And now we can go ahead and take a look at our right-hand side, our differential equations here. So the first thing right off the bat that we recognize here is that we are required here to supply a vector, just one vector of our dependent variables. So what we're going to need to do here is take our temperature and our concentration arrays and concatenate them, which means add them together. Not add them together, but basically add the last part of the concentrations to the first part of the temperature arrays and make them just one array here, because we need just one vector of dependent variables. So to unpack this, what I'm going to do is set the concentration values equal to vector from the first value, right? This colon here represents the first value, so value 0 to value n, and it doesn't include the last value here, so it'll go from 0 to 14. So the first 15 values of what this returns here will be our concentrations. And for our temperatures, we'll have the last 15. So back from n to the end, so n colon. Okay, so essentially what will be returned from our solve IVP is one big long array, and then we'll need to split it up into our concentrations and temperatures. And because we're, like I said, concatenating this into one array, we need to change our initial, what we're supplying here to solve IVP. So we're going to, whoops, so let me see here if I can, I'll just go ahead and put it in here. So we'll need to concatenate. So I'm not going to do it right now. Hopefully I spelled that right. But basically, if I wrote out NP concatenate our initial concentrations, well, I guess I can just do it here. Make sure we're good to go. Let's see here. Control V. Concatenate. NP has no attribute. I need to run this. Oh, let's see here. Concatenate. Well, obviously I spelled concatenate wrong. Let me see. Alright, sorry about that. I had an extra T in concatenate that I need to get rid of. But if we go ahead and run this, we can see we have 15 of our initial concentrations here starting out, and then we just add on the array of initial temperatures, 15 of those afterwards. So now that we have that, we can go ahead and look at our differential equations here. And what we're going to have is two different sets of differential equations. One, concentration and temperature for our first continuously stirred reactor, because that is just the flow rate going into the plug flow reactor, right? And then whatever is leaving that. However, the subsequent continuously stirred reactors are all dependent upon the previous previous CSTRs discharge. So whatever is leaving that CSTR is entering the next one. So what I'm going to do is go ahead here and comment this out and do both of them separately. So I have one for the first CSTR. And one thing also to note here is that this K here, reaction rate here, is we're going to have 15 reaction rates here because this is dependent upon temperature, right? And temperature obviously is not going to be the same. So that's one thing to keep in mind. But I'm just going to go ahead and copy and paste here a little bit. So again, this is for our first continuously stirred reactor. So at the very beginning of the plug flow reactor, we'll call this DCA naught for the first concentration of A here. And what we're going to have here is the concentration of A going in, which we know that's our stream going into the plug flow reactor. However, what is going to be leaving the first continuously stirred reactor is that first value in the concentration of A. And that first value, again, Python indexing starts at 0, so that will be the first value in the array. And likewise here, we will have the reaction rate multiplied by the concentration of A, leaving that first continuously stirred reactor. So, or whatever is in that continuously stirred reactor, right? Because it's continuously stirred. So whatever is leaving is the same as what's in it. So whatever's in it is the CA at 0 here. And like I said for K, this is going to be changing throughout because it's dependent on temperature. So K will also be, we'll have the first value of K here, so K in that first continuously stirred reactor. For our change in temperature here, it's a similar thought process, right? So we'll have our temperature going in to the plug flow reactor, and whatever is leaving, so we'll have, basically this is what's going in minus what's leaving, and what is leaving is T, the first value of T here in the array that we have. So that's T at 0. And likewise here, we will have the temperature in the first continuously stirred reactor minus the temperature of the coolant. And this K here will also be the first value. So the K value, the reaction rate in that first continuously stirred reactor, and then the concentration of A, likewise, the concentration of A in the first continuously stirred reactor. Now we'll have the remaining CSTRs. So remaining CSTRs, right? So this one is a little bit trickier. So let me just bring these up here. So what we have here, again, what is going into the reactor minus what is going out. Well, what is going in is Ca going from everything at the beginning, right? Going from the first element, so this colon is 0, and then everything up to the last continuously stirred reactor. So if we're on reactor 8, it's everything up to 7, right? So we want to exclude that last value. So basically what this colon to -1 here is, it's saying we're going from the first continuously stirred reactor and then everything up to the last value here before the next continuously stirred reactor. So it excludes that last value. I hope that makes sense the way I'm explaining it. But and then we'll subtract what is leaving. So everything, again, Python indexing starts at 0. So if we put in 1 here, that is actually the second continuously stirred reactor. So what is leaving is everything in that, and then after that continuously stirred reactor, so colon. And likewise for K here, we will have the K in that continuously stirred reactor and everything after, so 1 colon. And the same thing for the concentration of A, right? Concentration of A from 1, what is in that second continuously stirred reactor, and then everything up to everything after. Oops. Why all of a sudden? Okay, there we go. Okay, so now we have the change in concentration of A for all the remaining continuously stirred reactors. And we're going to have a similar thought process again for the change in temperature with the rest of the continuously stirred reactors. So the temperature going in to that second continuously stirred reactor will be the temperature at 1. And then for the subsequent ones, everything up to the previous temperature, right, in the previous continuously stirred reactor. So to -1. Whoops. Should be colon to -1. So the first continuously stirred reactor to the previous one, and exclude the previous one. Then the temperature leaving, well, that is going to be the temperature in that second continuously stirred reactor all the way up until the end, right? Same thought process as concentration. We have our volume, heat transfer. Let's see here, volume again. We have the temperature of the coolant here. Now this will be the temperature, the temperature inside that second continuously stirred reactor all the way to the end. And then we have K here. K will be from that second continuously stirred reactor to the end. And then likewise for concentration of A here, right? Okay, so now let me make sure we don't have any errors here, and we can go ahead and run this. We'll actually need to concatenate both our concentration and temperatures here. Let me go ahead and move this down. Okay, so now what I need to do is combine both this initial first value of the concentration with the rest of the concentration values, as well as the temperature, first temperature value with the rest of the temperature values in order to return it. So what I can actually do here is use something called np.r. What this is essentially it just concatenates values together into a row, hence the R. So if I go np.r dca naught and then dca, that will combine those together. And I will do the same thing for the temperature. So np.r, let's see, dt naught and dt, And then what we'll need to do is just concatenate both of these then into one total array. Return it just as one array in a single row with 30 values. So np.concatenate. Make sure I spell that right this time. Put a bracket at the end and close that. And let's make sure that this runs here. Okay, so we have our solve IVP here. We had already concatenated our initial conditions together. So let's run this and make sure that it goes through, and it does work. So now what we need to do is go ahead and make a plot of both the concentration and temperature profiles. What we're going to do is actually just plot each of the 15 CSTRs, one for concentration and one for temperature. So we have our plotting points for plotting purposes. So t-plot, linearly space them out. Instead of 500, I'm going to do 100 for this one. And what we can do here is we can actually take a look at our solution values here at t-plot. So if you look at the shape of them, oops, looks like I need to do this underneath. But essentially what we have, the shape of what we have is just one array of 30 values is what we returned here. So what we'll need to do is we need to reshape this right into two different arrays here with the size of n. So n is 15 right here, or in our case. So if we want to change n, we would be able to do that. And then what we need to do is unpack this into our 15 concentration values and our 15 temperature values. So we'll have concentration and temperature. And we'll go ahead and make our plots here. So what we'll need to do is basically run a for loop, and it'll plot for every CSTR 1 through 15. It'll plot the concentration and the temperature value in each of these timestamps here. So we have our fig is equal to make subplots. This is perfect. We already have it up because we're going to need one row and two columns for our concentration, CSTRs, and the temperature. So let's go ahead and make our for loop. So for I in range n, I'm just going to actually tab these over because we can just use these. So for our x points here, we'll have our linearly spaced out points here, t-plot. For our concentration here, for our first plot, we will want to run this for loop for everything from I. So when it starts the beginning of the for loop from the beginning all the way to the end. So I, I comma colon, right? All of the values. We'll put it in row 1, column 1. And what I can actually do here is we can name it concentration 1, concentration 2, concentration 3, so we can see all the different plots. And the way we can do this is if I put some squiggly brackets here and then put an F in front. Okay, so I believe we have what we need here for our concentration plot. We have our name, row 1, column 1. Let's go ahead and do our temperatures here. So same idea, we'll want to grab plot all of the temperatures here. So I to the end. Row 1, column 2, and this time we'll have our temperature. So temperature, squiggly brackets I, so we can get the individual CSTR's temperature, whether it's 1, 2, 3, 4, 5, 6, and so on. And again, F. Let's go ahead and see if we can get a plot here. See if we're not missing anything. Let's see here. Oh, we need to. All right, sorry about that. I think I just needed to indent my scatter plots more in the for loop. But I'm going to go ahead and update the layout. So I'm going to go fig dot update layout. I'm going to set the width equal to 1000 actually, and the height to 500, and we can see what this looks like here. Whoops, 500. So here are our plots. On the left here is our concentration, and on the right here is the temperature profile for each of the continuously stirred reactors. So if we go ahead and take a look at our concentrations here, we can actually zoom in just a little bit better. And I zoomed in, so it looks like this concentration of the first CSTR is not starting at 0.5, but all of these start at 0.5. And this actually makes sense because what happens here is that in the first, what we're doing is we're starting at, I think, a 0.5 moles per liter for the concentration of A inside the entire plug flow reactor, and then we're introducing a stream with twice the amount of the concentration of A. I think it's 1, right? So initially, the concentration of A in these first few reactors, I think up to like, looks like 3 or 4, they'll actually go up. And this makes sense because there's a reaction going on, right? So the concentration of A is going to go up. But again, because that reaction is happening, eventually these drop down and actually all eventually get to 0, and all of it is consumed. And then on the right here, our temperature graphs. Again, this makes sense if we look at the concentration, or excuse me, the temperature in the first CSTR. It's much higher than the rest of these other CSTRs because that incoming stream is coming directly into the first one, and all that reaction is happening, and by the time it gets to the last one, a lot of the A in the incoming stream has already been reacted. So this does definitely make sense. And one thing to note here is that for a plug flow reactor, we have reacted all of A and the concentration goes down to 0, whereas if you remember in homework 2 part C, when we had just one CSTR, it did not fully react, or not, it reacted, but it did not fully react all of A. So this will do it for homework 3. Thank you for watching.